Welcome to the UCSC Emeriti Group lecture presented by Bruce Rosenblum, Emeritus Professor of Physics. I'm Melanie Mayer, and I'm chair of the UCSC Emeriti Group. We're pleased to be able to present to the UCSC and Santa Cruz communities occasional lectures of significance by distinguished Emeriti faculty, and we appreciate Chancellor George Blumenthal's support in this endeavor. Now, Bruce wants me to introduce him by noting that his research has not always been at the far out edge of physics. So I want to say he has also carried out investigations in a number of more conventional but nonetheless important areas of physics during the course of his long career. For example, Bruce's PhD thesis at Columbia was on molecular physics. In a postdoc at UC Berkeley, he studied electrons in metals. Then, for a decade at a large electronics company, he worked on semiconductors, plasma physics, superconductivity, several engineering topics, and research management. When he came to Santa Cruz in 1967, Bruce worked on superconductivity and then a theoretical analysis of magnetoreception in animals, before focusing on the fundamentals of quantum mechanics. While at UCSC, Bruce has at times consulted extensively on technical and policy issues for both the federal government and industry. He's also served as chair of the physics department, acting provost of Stevenson College, chair of the Academic Senate, and acting dean of the Natural Sciences. He was a co-organizer of the Center for Innovation and Entrepreneurial Development, and for several years co-taught courses on entrepreneurship in our economics department. Though Bruce retired three years ago, his wife Phyllis says she hasn't noticed. In the winter quarter just finished, Bruce taught a seminar, The Observer in Quantum Mechanics, and this quarter he's co-teaching The Physicist in Industry, a course designed to help students get jobs and do well in them. Bruce's lecture tonight is based upon his new book, Quantum Enigma, Physics Encounters Consciousness, written with Fred Kutner and recently published by Oxford University Press. His talk is titled, The Quantum Enigma, Has Physics Encountered Consciousness? I present Bruce Rosenblum.
Thank you, Melanie. Okay, this is my lecture title, and our book title is actually more assertive, Physics Encounters Consciousness, but our point is that physics, we should not ignore this elephant in the living room. But my talk has a question mark on it, and it's addressed to you. Just modestly or arrogantly, I'd like you to decide whether physics has encountered consciousness. I'm going to tell of two experiments. Actually, demonstrations would be the better word, because the outcomes are well known and completely undisputed. However, the meaning of behind these talks, behind these demonstrations, is hotly disputed. And on the meaning, the particular expertise of physicists is not uniquely relevant. The non-physicist's judgment on seeing these demonstrations is probably equally valid and probably less emotional. sometimes I'm asked, define consciousness. Well, it's sort of like awareness. Susan Blackmore, in her book, Consciousness and Introduction, a textbook, halfway through the book says, notice, I haven't defined consciousness. And she says, people rarely do. Actually, here's one statement on that. I'm going to talk about quantum mechanics or quantum theory. I'll use the two terms interchangeably. Quantum theory, quantum mechanics, is basic to all of physics, and therefore all of chemistry, and maybe all of biology. Quantum mechanics is the most precise and the most battle-tested theory in all of science. String theories, theories of the Big Bang, all start with quantum mechanics. 1/3 of our economy is based on devices designed with quantum mechanics. Modern electronics is based on quantum mechanics, the transistor. The lasers, of course, are designed with quantum mechanics. MRI machines are basically quantum mechanical. But quantum mechanics comes with two mysteries. I'm going to tell you about them. But before I do, I give you a warning. When, 15 years or so ago, I proposed a course because I was asked to teach it sounds like I can wander around with this microphone. I was asked to teach, it was my turn to teach a course for non-scientists, our Physics for Poets course. And an advantage of that course is that you can teach anything you want, because you're not really, any physics you want, because you're not really preparing students for another course in physics. And when I proposed teaching the mysteries of quantum mechanics, one colleague objected. What he said was, though what you're saying is correct, presenting this material to non-scientists is the intellectual equivalent of allowing children to play with loaded guns. And I'm sympathetic with his concern. After all, if people see physics, the discipline of physics, saying crazy things, some people might become susceptible to all sorts of nonsense. All sorts of nonsense. There's a lot of that around. The movie, What the Bleep Do We Know? It starts out, it's the worst kind of thing, because it starts out with correct physics. Actually, a pedagogical exaggeration of the uncertainty principle. I won't ask who saw it. A bouncing basketball in several places at once. That's fine. But it goes on to show that quantum insights allow a woman to throw away her antidepressant medication. And then it goes on to the quantum channeling of the 35,000-year-old Atlantis god Ramtha. And then on to yet greater nonsense. I saw the movie, but I haven't read the bestseller, #1 bestseller for a while on Amazon, What the Secret? Oprah was a fan, and I understand it's now a movie, and it tells you that you can use quantum theory to gain wealth and happiness. I haven't noticed that experts in quantum theory are particularly wealthy or particularly happy. And I make no promises tonight. But partly embarrassed by this, I think, by the association with pseudoscience, that nonsense, most physicists avoid talking of the quantum mysteries. They've been called our skeleton in the closet. But if we talk about the meaning of quantum mechanics, it encounters consciousness, you'll see, and it stands as an elephant in the living room. And we can ignore the elephant for all practical purposes. But Fred Kutner, my co-author, and I think it's better to come clean. We consider our book an antidote to the pseudoscience. More about this, you can see more about this and the reasons for it on our website if you click on the link, a social responsibility. Our website's the same as the title of the talk almost. Modern quantum mechanics started in 1927, maybe. In 1932, John von Neumann, the father of modern computers, perhaps, wrote his well-known, his book, The Mathematical Foundations of Quantum Mechanics. And he showed that, very explicitly, that quantum theory's encounter with consciousness is inevitable, can't be avoided. However, for all practical purposes, we could ignore it. A couple of decades later, Eugene Wigner, who won the Nobel Prize for contributions to quantum mechanics, wrote that it is not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness. You don't need quantum theory to demonstrate the mystery. We can display it to anyone right in the laboratory. It's right in the experiments. For example, the doctrine that the world is made up, I got to make sure this is on the screen. Let's see how that works. Okay. The doctrine that the world is made up of objects whose existence is independent of human consciousness turns out to be in conflict with quantum mechanics, and I want to emphasize with the facts. Whoops, that doesn't work, but I have a pen that does. With the facts established by experiment, and we can go on to a more modern statement and see that even if quantum theory, I have to position this, even if quantum theory had never been invented, the experiments could be performed, and we would find ourselves unable to understand them. The experiments could have been performed, and we would find ourselves unable to understand them. The mystery is right there in the experiment. You don't have to know any quantum theory to see the encounter with consciousness. I'm going to introduce quantum mechanics encounter with consciousness with a little discussion of what bothered Albert Einstein. Albert Einstein, of course, more than anyone else, started quantum mechanics. And he paid a lot of attention to it. He said, I don't know how seriously to take this, but he said it, I have thought 100 times as much about the quantum problem as I have about general relativity. The most quoted comment of Einstein is that God does not play dice. But, you know, randomness, throwing of the dice, God's throwing of the dice, was not Einstein's real problem. He accepted quantum uncertainty. The dice quote, I think, is common because it's so easy to understand. Einstein's real problems are not easy to understand. They're not that hard to understand. They're hard to believe that, you know, when somebody tells you something that you can't believe, it's a natural reaction to say, I don't understand. But maybe you do understand. It's just that you have trouble believing it. Here are Einstein's two problems with quantum mechanics. Now, I seem to have no. I can say them and I don't find my right overhead, but it's nicer to have the right overhead. Okay, what Einstein said was I can't believe quantum mechanics because I believe the moon is there even when I'm not looking. The other thing he said, that a reason that he couldn't accept quantum mechanics, because quantum mechanics involves spooky interactions at a distance. Let's look at first the demonstration of Einstein's problem with the reality, the meaning of his moon quote, spooky later. See if you can feel Einstein's pain. Leading physicists today do. It's hard to demonstrate the creation. You know, Einstein said the moon isn't there. Quantum mechanics says the moon isn't there when I'm not looking at it. It's hard to demonstrate this non-reality of the world with larger things, certainly not with moons. But Einstein was really only half joking about the moon. Quantum mechanics does deny a real world independent of its observation. The demonstration that bothered Einstein is readily done with photons. Atoms or big molecules or an object with several thousand atoms is trickier, but it's done. The demonstration of the non-reality using photons is available as a lecture demonstration. It costs $5,000. Let me talk about our demonstration. What I do is I'm going to prepare a set of box pairs of boxes. What I'm going to do is send in an object from the left. It could be a photon, an atom. Hey, by the way, we can see individual atoms today with naked eye. I can see an individual atom. We could put it in a little vacuum trap and shine the appropriate laser light in it, and you can see the glint from the atom just the way you see a dust mote in a sunbeam. But that's an aside. We send in an object, one object at a time, one object, and it goes into a pair of boxes. I don't care how, it doesn't matter. Let's just say we have a black box, and I send in an object, and when I know it's in this region, I close the boxes. Okay? What I do is I collect a four sets of box pairs, set A, B, C, and D. Each pair one is green and one is blue. And with the box pair set A, take box pair set A, and I do an experiment with it. Let's see. What I do is I take the box pairs here, I take each pair and space it by a distance s. Space it by a distance s. And then I open the two boxes over here at the same time. And I find that an object lands someplace on the screen. Plink. And then I take that box pair and put it away and take another box pair from set A and place it at the same place, separated by distance s, open them both, and plink, another object comes out. And what I find is, and here are the box pairs that I've already used, they're empty, and what I find is that the objects land in certain places, but the places they land, the allowed places and the forbidden places, depend on the spacing of the boxes. The larger the spacing of the boxes, the closer the clumps of places they land. Each object knows, in a sense, the spacing of its boxes. Each object follows a rule depending on the spacing of its boxes. It knows how far apart they are. Therefore, we can be assured that something of each object is in each box of its pair. The objects are distributed over both boxes. But now, instead of doing this so-called interference experiment, I won't tell you why it's called that, we can do a different experiment with box pair set B. We can do an experiment with box pair set B and just look in the box, either box of each pair. And what you will find is a whole object in one box of its pair, and the other box of its pair will be totally, absolutely empty. Okay? Hey, it seems that it would seem that the objects in set that used for set A were the kind of object that were distributed over both boxes, while the objects that were in set B were concentrated in a single box. What would have happened had we looked inside the boxes in box pair set A? Would we have seen a whole object in a single box and the other box was empty? Hey, we can't do that experiment because the objects have already come out and landed plink on the screen. But we have more sets of box pairs. Okay? So with box pair set C, I now let you freely choose with your conscious free choice what to demonstrate. You could choose to look in the boxes and demonstrate, prove that each object is wholly in a single box, or you could choose to do this experiment and prove that each object was distributed over both boxes. So you could do this as many times as you want, always demonstrating the situation that you freely choose. You can't choose which box the object will be in or which allowed place on the screen the object will land. But by your free choice, wasn't it free? Didn't it involve your conscious free choice? You could demonstrate either of two contradictory things. Question: what was the reality of the situation of the objects in the box pairs just before you chose to demonstrate one or the other? Were they wholly concentrated in a single box, which you could prove, or were they distributed over two boxes, which you could prove? Here's quantum theory's explanation of that. Before the quantum theory's explanation, see, I didn't use theory at all, just an observation. And here's quantum theory's explanation. Before the boxes were opened, each object was in I'll write it a superposition state. It was equally in both boxes. It was in both boxes at the same time. It was in two places at the same time. And I indicate that by having a little sort of object in each box there. And but when the object, the spread out object, the object was in two places at one time, hits the screen, it's observed, and it collapses. Is the word that John von Neumann introduced, collapses, and into a single place. It wasn't in a single place before it was observed. It was in two places at once, but after you look at it, it's always in one place or the other. And the same thing is true here. Here the object was in a superposition state, and here it has collapsed. And here are all the boxes that have been collapsed. What did the observation? Who did the observation? What did the observation? Did the screen? What collapsed the object into a single spot? Quantum theory does not answer this question. We'll have to deal with it by various interpretations of quantum mechanics or quantum theory. You know, instead of pairs of boxes, we could have put an object in a set of 4 boxes, or 40 boxes, or 4,000 boxes. But a look in the boxes would determine where each object was. But you could have proven that it was not there before you looked. Somehow, looking puts it there. Hey, do you see Einstein's problem? There wasn't a reality before he looked. So he said, gee, what quantum mechanics is saying, that there's no real world out there independent of its observation. You know, the explanation I've given you of quantum mechanics, this superposition and collapse, is standard, is the standard textbook quantum theory explanation. It's essentially undisputed. At a recent meeting, and it's demonstrated so far, though, only with small objects, you know, photons, atoms, collections of atoms, things made of 1,000 or more atoms, but not really big things. At a recent meeting, Anton Zeilinger, an Austrian physicist, who put a big molecule, a so-called buckyball with 70 carbon atoms, in 2 places at once, was asked, what limits the size of the object you can do this with? And his answer, only budget. Quantum theory says it can be done with any object, though not with large objects for practical reasons, technological reasons. Princeton quantum cosmologist John Wheeler is explicit. Quantum mechanics applies to baseballs as well as to atoms. According to Heisenberg, it applies to stones as well as to electrons. Quantum mechanics denies the straightforward existence of a real world independent of its observation. Einstein had trouble with quantum mechanics because he insisted that there was a real world independent of its observation, that the moon was there even when he wasn't looking at it. Erwin Schrödinger was bothered too. The fundamental equation of quantum mechanics is Schrödinger's equation. If quantum mechanics is right for atoms, he insisted, it's got to be right for things made of atoms. If an atom could be in a superposition state in two conditions at one time, both spread out in two boxes at one time, two conditions at one time, so could a thing made of atoms. If, for example, a Geiger counter was in one of the boxes, if you found the atom in the box with the Geiger counter would have fired, gone click. If you found the atom in the other box, the Geiger counter would be unfired. After all, a Geiger counter is a device that obeys the fundamental laws of physics. It obeys quantum mechanics. Therefore, according to quantum theory, according to quantum mechanics, before you look at this Geiger counter or at the atom, the Geiger counter is in a superposition state. The atom is simultaneously in both boxes, and the unobserved Geiger counter would be both fired and unfired at the same time. Schrödinger told a story that he felt would show that all this was absurd. Schrödinger's cat. First of all, this is just a thought experiment. Schrödinger was an animal lover. He called this a hellish contraption. For all practical purposes, it's not doable, but it's the principle that counts here. Our Geiger counter is in this box with a cat, and if I display an atom that we sent in by crests of a wave, it's in both boxes. And we could have proven that if we didn't have a cat disturbing things. But the atom is in both boxes. If the atom is found in the box with the Geiger counter would have to be clicked. And this particular Geiger counter, when it clicks, it pulls a lever up and pulls a cork out of a bottle of hydrogen cyanide gas and poisons the cat. A thought experiment, remember. But unobserved, before you open the box and look in, the unobserved cat is in a superposition state, simultaneously alive and dead. If you look in and find the atom in the top box, you'll find the atom alive. If you find the atom in the bottom box, you'll find the Geiger counter lever clicked, the cork pulled, and the cat dead. If you look and find the cat dead, are you guilty of killing the cat? Not really, unless you put her in the hellish contraption in the first place. Her collapse into dead or alive is completely random. You're looking, according to quantum mechanics, remember, the most battle-tested theory in all of science, would cause the cat to become either dead or alive. Your looking would cause the cat to become either dead or alive. Is that crazy? Hey, here's something crazier. Suppose 8 hours after sending in the atom, you open the box and look. If you collapse the cat into the dead state, a forensic pathologist could tell you that the cat had been dead for 8 hours. If you find an alive cat, it would be a hungry cat, unfed for 8 hours. According to quantum theory, your look not only creates the reality of the cat's state, it creates a history appropriate to that state, backwards in time. Schrodinger's point was that this is absurd. He, like Einstein, had trouble with quantum theory, his own quantum theory. Let's go on to illustrate, to talk about Einstein's second objection to quantum mechanics, its spooky action at a distance. In 1935, when quantum theory was about a decade old, Einstein proved that quantum theory's observer-created reality could only be true if what someone chose to do in one place could instantaneously affect what happened someplace far away without any physical force. Einstein argued that since one can't accept what he called voodoo forces or spooky actions, quantum theory's observed reality must be wrong. Einstein's famous paper, written with two young colleagues, Rosen and Podolsky, is now called famous as EPR. We're told that when it arrived in Bohr's institution in Denmark, it came as a bolt from the blue, a complete surprise. Apparently Bohr never realized that quantum theory involved such spooky actions. Niels Bohr, quantum theory's principal defender, supposedly paced the floor for weeks trying to figure out what was wrong with EPR. Finally, he admitted that the EPR logic was sound, but he insisted quantum theory was okay. Spooky interactions do exist. He called them influences. We now call them entanglements. For 30 years, whether or not these entanglements were physically real was considered merely a philosophical question. No way to test it, no way to see them. But in the 1960s, John Bell, on sabbatical from his day job as a particle theorist and accelerator designer, developed an abstract mathematical proof called Bell's theorem, showing that the existence of spooky interactions could, in principle, be tested. In a shared taxi ride on the way to a conference in Emeriti, Italy, Bell told me that he had not expected an actual test for many, many years. But in fact, just a few years after Bell's proof, John Clauser, a graduate student at Columbia University, had a brilliant idea. And at Berkeley as a postdoc, he convinced Charles Townes to support his work to look for quantum theory's spooky actions. Clauser expected to show that they did not exist, that something was wrong with quantum theory. If so, it would be quantum theory's first wrong prediction, and perhaps a Nobel Prize for Clauser. To his disappointment, Clauser proved that spooky interactions, quantum entanglements, were there in just the way quantum theory predicted. EPR's denial of observer-created reality fails. It was based on the assumption of no spooky interactions. John Clauser showed that any two things that have ever interacted are forever entangled. And since they interact with the rest of the world, there exists a Universal connectedness, whatever that means. These entanglements, Einstein's spooky interactions, are today the basis of quantum computers. What someone consciously chooses to do in Singapore or on planet Saturn can instantaneously, but randomly, influence what happens in Santa Cruz. The influence is random. There is no remote control. Unfortunately for John Clauser, in the 70s, there was a strong prejudice in physics departments against exploring the mysteries of quantum mechanics. It still exists to a smaller extent. But then, Clauser could not get a university position to work in the field that, to a large extent, he launched. So, how does physics deal with observer-created reality? From the beginning of quantum mechanics, we learned how to ignore this elephant in our living room. We interpret quantum mechanics. Our original, orthodox, standard textbook interpretation of quantum theory is Bohr's quantum mechanics. Bohr's Copenhagen interpretation. It came in 1927, almost immediately after quantum theory. It has many versions, and here's just one version. It is wrong to think the task of physics is to find out how nature is. Physics concerns only what we can say about nature. Though it works for all practical purposes, quantum theory works for all practical purposes, Bohr had to redefine the role of science. To explain the world is no longer the goal of science, just to say what happens in the experiment we actually did. Einstein objected to this, saying he came into physics to learn God's thoughts. In his Nobel Prize acceptance lecture, Gell-Mann accused Bohr of brainwashing generations of physicists into thinking the problem was solved. I admit brainwashing several hundred physicists myself, somewhat at least, by my not fully presenting the mysteries in quantum mechanics courses I've taught. There's too much else to cover. And after all, we have to send young physicists out with clean, washed minds if they're going to work on practical stuff and not get bogged down with philosophy. The Copenhagen is criticized today, in particular the criticism, shut up and calculate. Today, several interpretations contend with Copenhagen. We mentioned 9 of them in our book, some with just a paragraph or 2. Did I mention my book's author, Fred Kutner? I should. Responsible for half the work. I'll just mention 2 interpretations. One is called the Manyworlds interpretation. It's also called, by the way, the many minds interpretation. There is no single world. Everything that can possibly happen actually happens. You both find the atom in the blue box, and you, in another world, find the atom in the green box. And yet another you decided to do an interference experiment instead of looking in the boxes and proved the atom had been in both boxes at the same time. When you found Schrodinger's cat alive, another you found it dead. That first you went on to feed the hungry cat, and the other you buried the dead cat. Does that sound silly? Well, the Manyworlds interpretation is a bit bizarre, but it's taken seriously by some quantum cosmologists. And it is very strongly defended as the most reasonable view to take by some quantum computer experts. Another view, taken seriously by some, is the transactional interpretation, in which everything is really okay if you just accept the fact that your future determines your past. Your observation now of the cat alive caused the atom that might have triggered the Geiger counter to pull the plug on the poison gas to actually go into the other box, backwards in time. In the spirit of this view, here's a famous sketch by quantum cosmologist John Wheeler. That's an eyeball on the left, and what's on the right? That's, he's a quantum cosmologist after all, that's the Big Bang. Our looking at it caused it. Does looking back now give reality to what happened then, was John Wheeler's question. Interpretations of quantum theory both explore what nature is trying to tell us, but also show why, for all practical purposes, we don't have to worry about the mysteries. The big things that we deal with in everyday life will always behave reasonably in the world you happen to be in. Interpretations of quantum mechanics both explore what nature is trying to tell us and also show why, for all practical purposes, we don't have to worry about anything. Big things will always appear to behave sensibly. But I like John Bell's admonition. The new way of seeing things is likely to astonish us. He had no idea what the new way was, but you know, we might approach this unresolved enigma physics has encountered with open-minded modesty. We don't really understand it after all. Fortunately, very little physics background is needed to grasp the enigma. No physics background is needed to grasp the enigma. It's right there, demonstrated to anybody in the laboratory. In fact, the particular expertise of the physicist is not uniquely relevant. Unfortunately, the profound, unresolved enigma is easily exploited by the purveyors of pseudoscience to make money by promoting garbage. You know, Bleep and The Secret both were very successful at doing that. But just debunking such nonsense doesn't work. Debunkers never get much attention. It's probably best not to hide the enigma, not to hide our skeleton in the closet. Unfortunately, we physicists find it embarrassing to see our physics connected with something as mushy as consciousness. It's been pointed out that physicists have long had a special loathing for admitting questions with the slightest emotional content into their professional work. Question: should we teach the quantum mysteries in our physics courses? It's disputed. The analogy with sex education comes to mind. Okay, thank you.
We'll have an opportunity to ask questions from the audience. There is a microphone here and one over there. And I'd ask you please to limit your questions to one at a time so everybody gets a chance. And then if you have other questions, we'll come back to you. You want to start?
The focus of your presentation and the presentation of the enigmas hinges on human observation of events and the attempt to interpret what is happening.
Right.
But if we think quantum mechanics truly describes microscopic processes, and we surely believe that these processes have been going on for billions of years,
Yes.
and billions of years before there was any consciousness to even consider, then how can consciousness be critical to any of it?
Good question, and I don't know the answer. When Eugene Wigner drew his picture and asked his question, it was a question. I don't have the quote written out in front of me, but I'll paraphrase that the universe came into existence because we observed it to exist. It doesn't matter that the observers came along 14 billion years later. The universe exists because we observe it to exist, roughly quoted. That was Martin Rees, professor at Cambridge, Britain's astronomer royal. There's a story behind that, I can tell, but I won't.
I'm going to use the microphone back there or here to ask a question.
My name is Michael Knollenberg. I've been teaching quantum mechanics.
A lot in the microphone.
I've been teaching quantum mechanics and doing research in the subject for the last half century. In fact, Bruce quoted John Bell, "The new way of seeing things will astonish us." That quotation actually appeared in a joint paper that I wrote with John Bell 40 years ago. Now, a lot of our understanding of quantum mechanics has changed a great deal in the last 40 years. And much of what you've heard we seem to be stuck in the past. Concerning the question raised, which I also was going to raise about the universe, the quotation is attributed to Martin Rees, who is the royal astronomer in England, currently the president of the Royal Society and probably one of the most prestigious astrophysicists in the world. And the question raised is, how come the universe, which existed now for billions of years, there were no observers, nevertheless, they look back. So Martin has been frequently a visitor here in Santa Cruz. We know him well, so naturally I send him an email.
Sorry to interrupt. What is your question, please?
I am making a comment first. Is that okay with you?
Yeah,
Can I
please.
finish my comment?
Yeah, please.
My comment is that I asked Martin, where did he make this comment? And he was totally astounded, completely surprised. He said, "I never made such a comment." I mean, he's a very rational person.
He said he didn't recall it.
That he would. It turns out that the comment appears, in fact, does appear in an article by Martin Rees under that diagram. But it's really a Wheelerish comment. Martin, it's like in your book, the publisher probably writes the outside pages of your book, and you have very little control.
No.
But sometimes appears. Anyway, Martin totally denies any such statement. And the fact is that all by itself makes you extremely suspicious that consciousness has to do anything. Anyway, the message I want to let you know is that what you heard here about consciousness is the belief of Bruce and his co-worker, by the way, was one of my first graduate students here. Fred Kutner was my PhD student. That's their belief, but it is not the views held by the scientific community. You can, incidentally, rather than a skeleton in the closet, I just did a little search in the literature. There are hundreds upon hundreds of papers on the foundations of quantum mechanics. I looked at about 70 pages of references to this subject. It is widely discussed. There's no skeleton out here. Everybody discusses this ad nauseum. But nowhere today, I'm talking about the 21st century, are these notions of consciousness in the literature. I mean, virtually all the respected physicists, in fact, deny completely that consciousness has to do anything with the subject. Thanks.
Would you like to comment on that, Bruce?
Sure. Let me comment first on the accuracy of my quote of Martin Rees. It wasn't verbatim, but the context was right. When we put that in our book, Michael got very upset and wrote to Martin Rees, who wrote back and said he didn't recall it, but, and Michael sent an email out to everybody in the physics department, but we had to send an email out to everybody in the physics department giving a reference to the journal in which, indeed, Martin Rees said it. It's not unusual that physicists who say these odd things back off. They worry about it. By the way, I don't want to sell our book, but if you talk about, we didn't attribute the quote to Michael and John Bell and Michael, because we knew that Michael didn't like it, but John Bell did, and I spoke to Michael knew John Bell before I did, but I knew John Bell after he did. I knew John Bell very well the year before he unfortunately died prematurely. And our dedication, the dedication of our book is to John Bell. And if you read the dedication, there's a quotation of John Bell's from the last paper he ever wrote. And I think you'll be convinced that what we're saying is certainly John Bell's thinking, and that John Bell is probably the leading quantum theorist of the latter half of the 20th century. I think Michael's not quite right about whether consciousness and quantum mechanics are connected. Go on the internet, Google quantum mechanics and consciousness. You'll get hundreds, if not thousands, no doubt, of references. Unfortunately, many of them screwball. That's the sad part. You'll get many sound references too. But let me say, physicists are emotional about this subject, much more emotional than non-scientists, non-physicists. And that was an example of it.
We have another question over here. Yeah.
Hi, my name is Zack. I'm just a second year here at UC Santa Cruz. As I can see, there's a lot of tension between scientists and non-scientists on the issue of consciousness in quantum mechanics. And I just had a question for you. I remember reading a Wikipedia article about quantum consciousness theory maybe last year, and it had some references to some pretty prestigious quantum theorists. And one of the main points of this article was that, like you said, quantum consciousness permeates into physics, chemistry, and then biology. One of the main points was that a basis for quantum consciousness in our brain would be that the neurons that communicate with each other don't really communicate with each other on a chemical basis, on a neurotransmitter basis, but they communicate with each other on some sort of nanotubule basis. I don't remember the word, but I'm wondering if you know anything or can elaborate on that theory or idea that our
Sure.
neurons communicate with each other on a quantum mechanical basis.
Sure. Two fairly eminent physicists, one, Henry Stapp at Berkeley, has a theory which we devote a paragraph or two to in our book that I don't want to expound, but yes, he talks about quantum effects in the brain and quantum Zeno effect. I don't, how observation can, related to watch pot never boils, if you observe a quantum state continually, it doesn't change, and how intention can collapse quantum states in the brain, and since everything is entangled, that changes things outside. I don't want to go into it in detail. Another famous theory, these aren't interpretations of quantum mechanics, these are modifications, these are theories, speculative, and presumably testable. Another well-known one that you probably encountered in Wikipedia is by Sir Roger Penrose, professor at Cambridge. Is it Oxford or Cambridge? I think it's Cambridge. And Sir Roger Penrose, he, perhaps one reason he's famous, he was Stephen Hawking's thesis advisor. And he has another theory of consciousness that is in the brain that actually is rather specific, and he's a gravitational cosmologist, quantum cosmologist, and so his theory of consciousness involves gravitational cosmology, that if an entity, a molecule in this case, changes its shape enough that its gravitational potential changes, it can cause a conscious event, an instant of consciousness, I think he calls it, quoting William James. And he has done work with someone else who suggested a particular molecule, the tubulons, in the structures of the neurons and other things, a certain kind of protein that does have just the right shape and presumably gravitational interaction to do this. Again, the theory makes predictions, but they haven't been tested. I think this is what you're talking about. So yeah, these things are talked about by legitimate physicists, but not frequently. It's embarrassing. It's scary. It's hey, at one time, back in the 50s, Banish Hoffman, a biographer of Einstein, said that it would be dangerous to the career of any non-tenured physics faculty member to show any interest in the fundamentals of quantum mechanics. That was in the 50s. McCarthy era, I don't know if that had anything to do with it, but things are less so today, but still so today, that in the 70s, Clauser couldn't get a job in the physics department because what he had done, brilliant work, but there was a lot of prejudice against it. And there's still prejudice against it, that if I were an untenured physics faculty member, I'd be a little bit hesitant about publishing that book. I'm sorry.
I'm Todd Whipke.
Todd, hi.
There's the act of observing in connection to the brain is a biochemical transformation in the brain, that we know we observe something.
Somehow.
But we can also think we observe something by imagining. And if we get the same biochemical effect in the brain, it's as though we observe. Now, and this happens when we dream, because sometimes it's very real. And when we wake up, we're confused about whether it was real or not. How does that interact with whether the particle will be in one box or another?
Wow. Well, my first answer is I don't know. My second answer is you have to choose to do the experiment and then actually do it. And so what happens in dreams is just a dream, I guess. I don't really know how to answer that question.
We have time for one more question. This person here.
Thank you for coming today and broaching this topic with us. I know it's very controversial, and I must classify myself as a non-scientist, but definitely an enthusiast in the questions of natural philosophy, which I think was what physics was called way back when. And quickly, I just want to ask if you see any relevance to ancient wisdom traditions, such as Tibetan Buddhism, that would tend to lend credence to the idea that when we observe ourselves, that is the only time that we exist as an independent entity, and thus that consciousness itself may be a quantum phenomenon in the sense that it's independent of the observer, that you know, I know this is going to sound like nonsense to some, obviously, because I'm definitely not a rigorously trained physicist and definitely a lay philosopher, but I have gleaned enough eclectic knowledge to have some deep contemplations on this, relatively deep anyway, and I'm just trying to suggest that maybe there might be hope that ancient wisdom traditions could someday be melded with the questions of physics. And do you have any thoughts about this?
Well, first of all, I claim very little expertise in this area at all. I just don't know. And Freud talked about the feeling of universal connectedness, or the oceanic feeling. Certainly the Eastern mystics talked about universal connectedness before we knew about entanglement. Does that mean that they predicted quantum mechanics? Well, absolutely not. There is a book that still sells, apparently, Fritjof Capra's Tao of Physics. And it's not a crackpot book. It's not pseudoscience. Fritjof Capra is a friend. It was once a postdoc at Santa Cruz, I think a postdoc of Michael's. And when he wrote that book back in the 70s, I guess, the Tao of Physics, maybe some people here even heard of it. What he does is he talks about Eastern mysticism, and I'm told by somebody who knows about it that he says reasonable things, and then he talks about quantum mechanics, and he certainly knows his quantum mechanics. And I once said to Fritjof, gee, do you really think that the Eastern mystics predicted the existence of quantum mechanics? And he said, no, I never said that. I'm just comparing quotations of the Eastern mystics with quotations of quantum mechanics. And I said, well, Fritjof, a lot of people think that's what you're saying. And he said, well, no, I didn't say that. And so I don't know. It's, did you have, I could think you could feel universal connectedness in some sense without ever knowing about quantum mechanics? Is that
Just a quick follow-up. The definition in the Vedas of consciousness in Hindu scriptures is the ability to self-refer, but the Tibetan Buddhists would go beyond that and say that it's basically a non-local, ineffable, or what physics might call isotropic phenomenon. So,
you know, I can't. I don't know.
okay.
I just.
Thank you all for coming tonight. We have refreshments back here, and you can continue some of the conversation over refreshments if you like. Thank you, Bruce.
Thank you.